Next, I'd like to welcome Scott Shih. He's the co-founder and CTO at ZettaBlock, a startup building essential data infrastructure for Web3. Scott led the cross-functional initiative at Uber to build their safety report, which was one of the most important data as a product releases ever made to the public in the United States. Scott's here to talk about the data journey of the Uber safety report and how he and his team designed, built, and maintained the complex data system needed to classify critical safety incidents. So, with that, I'm really excited to hear about the learnings that he has from that journey. So, take it away, Scott.
Hello, everyone. I'm Scott, co-founder and CTO of ZettaBlock. Today in this talk, I'm going to talk about very interesting and unique data quality project, the 2-year journey of Uber safety report. Before ZettaBlock, I'm the founding engineer for Uber safety data and led a cross-functional initiative at Uber to build Uber safety report. The project grew from myself to 200 full-time employees within a year. The goal is actually quite a simple one. Out of the billions of data points, identify all the data points related to critical safety incidents. At the end of this journey, we found around 6,000 critical safety incidents, so it's 1 in a million possibility. This is one of the first kind in the travel industry and a very unique data problem. From the 2017 to 2019, the safety team is the most important team in Uber. Why is that? Because there are nearly 4 million trips happen every day in Uber in the US, and that's actually 45 rides every second. But we only have a rough idea of how many critical safety incidents happen on Uber. Unlike the safety in Facebook, Twitter, or Airbnb, Uber actually connects strangers physically together in a small box for a long period of time. So this actually creates a possibility of serious interperson conflict like physical altercation or sexual misconduct. So we are working towards the goal Uber should be the safest way to get a rider back home or to a dangerous place. But we also have a case that it's the most convenient way to actually rob a car for a malicious rider. So when the CNN report is out, we don't even know how many of the serious incidents like sexual misconduct actually happen on Uber. So Uber is a data-driven company. Actually, it's probably one of the best data-driven companies in the world. If you think about the dependent supply, the surge price, and how we dispatch drivers are all data-driven. Safety team is the most important team in Uber at that time. Then the safety data team, which I co-founded, is actually the backbone to provide a solid foundation for the rest of the safety team, operation team, and business intelligence team to apply machine learning and AI to make data-driven decisions. So I initiate, design, build, and maintain a complex data system to systematically support needs from stakeholders of several organizations. From a 10,000 feet view of the problem, there are close to 1 billion support tickets, close to 1 billion support tickets. Majority are communication between riders to the platform or the drivers to the platform. And we are trying to use the taxonomy classification to map the report to the corresponding category, no matter it's, for example, physical altercation, or it could be a dangerous driving, dangerous driving. Then the data analyst could identify how many serious incidents we have on Uber, when and where they happened. So the project is initialized from executive level in May 2018. Our engineering team built the tool within a week to support the MVP, the operation. We first classified the first few like 1,000 data points ourselves. Then we found a big problem. The underlying taxonomy classification, which we use from National Sexual Violence Resource Center, a third-party nonprofit organization, is actually very inaccurate and very ambiguous. The reason is that comparing to the travel industry, Uber at that time is the only platform that capable of get all the data or all the incidents in one place. So we have all the data. We can make data-driven classification, data-driven result. But that's actually not available to this nonprofit organization. So without this data, it's actually a lot of classification and hard to define. So that's why we actually redefine the classification standard together with the NSVRC. So once the taxonomy classification is standardized, then we involve highly trained special agent to classify 500,000 data points. So 3 months into the project, we we cracked like 500,000 data points, but we discover more problems than answer to the CNN. Why is that? Just take three most important problems to give you a flavor. First is, how do we crack the obviously wrong tickets? Do we crack it from social truth web application, or do we crack it from analytical database, just from the data level? And second, what is considered an incident? Well, I'll show in the following slides why this is actually a difficult problem to address. Third, do we keep two sets of data, one for public release and one for our private use? Or do we actually use the same data set as classification results? So this is a very difficult to answer problem. So there were several rounds of discussion following the principle, the doing right thing, which is actually everyone just agrees this we should do the right thing. So then that's why we decided to 10x the results. No matter its number of operators, number of special agents, engineers, analytics, and we basically virtually get unlimited results to have completely transparency and crack data from the social truth web applications. Then we have 6 organizations across Uber went over, classified, and cracked all the safety incidents in US and Canada from 2017 to 2019. So let's actually look at like individual safety incidents level. And let's look at what's a life cycle for one safety incident. So let's take a look at a much simplified life cycle. If I don't feel safe about one of the trips I took in the past, then I could report incidents to the Uber support agent team, customer support team. We actually have several tiers of customer support team internally, but let's actually simplify this scenario. When customer support team receives this information, they will message the corresponding party to actually to get more information and have a better understanding of the situation. They will also escalate to a JIRA ticket if it's considered as a serious incident. And our special trained agents will take over the case and handle it separately. Usually, they will message the other party to get a clear picture of the situation. And also, it will have some back-forth communication message, and we will combine with the trip GPS data, audio, and dash cam data to cross-verify. And the things can get really complicated if it's a Uber pooled rides. You have several riders in the Uber pool. And then if the involved party beyond the Uber platform. So if, for example, maybe there is a third-party person actually involved in the incident. So apparently, it doesn't make sense to have each ticket defined as a one safety incident, because in this case, even if it's a one dangerous driving ticket, they may have like 4 tickets already. But what defines an incident and what defines a ticket? How about an incident has several JIRA tickets? So this is actually a several difficult question to answer. Additionally, at the end, we found that only 3 in a million ride or 1 in 10,000 tickets are serious incidents. But how do we find and classify them? And the initial data set is actually classified by the ever-changing auto-date standards. So in this case, not only does the data outlive the code, but also data outlive the classification standard. We tried different NLP models, but it feels hard on the classification. So we only use NLP, natural language processing, to escalate potential safety-related tickets. And there are much details, and devil is in details. For example, we found that there is a major regional difference. No matter it's a standard or it's a different scenario, the region difference is actually very obvious. And also, even in US and Canada, there is a lot of language difference. We do find a lot of tickets of foreign language, which special agent was not able to handle. So we actually need to repipe it into agent spoke the same language and let them to actually audit the ticket. We also have product line difference. At that time, Uber has Uber trip, Uber pool trip, and then Uber bike, and Uber Eats. So the product line is actually has a strong difference in each because of the underlying business is different. We also have different safety standard, but we actually unify them to a global safety standard. That's the process actually took several months as well. And we do have culture difference as well. It may consider an offense in one region, but it's not considered offense in another region. So this is generally speaking, this is a process owned by the operation team. The whole top priority is to make sure to act quickly and deactivate the reported party if involved in a serious incident. So the category classification is afterthought in this process. So once we go beyond this process, it steps into the category, step into the territory of safety team. And we're going to use the classification from the initial report and map to a category we actually use for monitoring and for use to report in the Uber safety report. So since we basically make a data-driven standard and improve the standard and monitor and change and work with a nonprofit organization for this. And each time we improve the taxonomy mapper, all the incidents actually need to be reclassified. Otherwise, the data will be outlive the standard. And we need to reclassify them use the latest version of taxonomy mapper. So this guarantee the data is always live with the current standard. And we internally build a GitHub-like version taxonomy mapper just for this use case. And this provides a base point for sampling and quality assurance. Okay, so let's look at from high level how an audit flow look like, architecture look like. So this is a high-level abstraction of how audit flow architecture look like. From the source to truth data is support tickets and Jira tickets. The data is ETL to analytical database. So the QA manager could initiate a batch audit by writing SQL, specify a list of tickets, or tickets met certain criteria, like for example, it could be US and Canada 2018 April 1st data, and then it could be related to initially classified as dangerous driving and go to the audit pipeline. The system will generate audit tasks and assign them to the agents. Usually we have more than one agent look at ticket. So the agent will look at the ticket and select the correct category and answer some other questions as well. The response will be recorded and written back to analytical DB, then build a lot of logic controller to enforce the life cycle of the incident. The response is consolidated and used to correct the data from source. Now we have an eventual consistent data system. Basically, can look at how many serious incidents we have on Uber. There are 200 full-time employees work on actually 35 million audit to make sure all the safety incidents in US and Canada are audited and classified correctly. Let's look at how a single audit looks like from an agent perspective. From left side, you have Jira tickets or serious safety incidents. List all the details like when the incidents happen, where the incidents happen, who is the driver and rider involved in these incidents, what are the data points, photos, and videos we have, and who is the agent actually handle these tickets, and what are the GPS information for this ticket. From the right side, agent could select what are the categories of the incidents and if this incident is valid or not. Since the underlying technology is flexible enough, this is actually similar to Uber internal version of Skill.ai. So the tool I built actually in this case is also used in several other projects like machine learning labeling, human in the loop project, or the driver ID identification, human in the loop project. For the driver ID verification, we basically use a photo verification algorithm. And if algorithm is not quite sure if the photo mapping this driver, then the verification is sent to a human in the loop audit. So it's actually used in several other projects as well. Okay, so let's look at a life cycle. Let's go back to the Uber safety report. Let's look at the life cycle of one incident. In this case, actually, it shows a real world scenario, like the real life cycle of the ticket of the ticket, and it's actually beyond humans' capacity to track the life cycle of millions of incidents. That's why we define finite state machine and write controller code to monitor the state for each ticket, enforce the state transition for each and every single ticket. Simplicity is actually the most important and first principle. We practiced and followed. And so this is actually, this finite state machine is the simplest form, but it's still so complicated. If you look at this, is there like 15 states and more than 20 transitions. The complexity mainly comes from the natural fact that we have both incidents and tickets, and there are different types of tickets. And tickets could be changed from source at any given time, because a lot of tickets actually being changed even after half a year after an incident. They may have some new findings, or the driver may report something else after an incident. So the state, if that happens, like the ticket is changed from source, the state need to be reset and ticket need to go through the whole process again. This is a final data site, looks like, well, but a much simplified version. All data linked towards the safety report incident fact table. So in this fact table, you can see it's linked with all the evidence. How many of zero tickets is linked with this incident? How many of support tickets are linked with this incident? What life cycle it goes through, transition, the whole life cycle it goes through, like what's the before state, what's the after state, what was the agent voting at that time, and how does it reach a consensus? And then it's also linked with the trip information, like linked with the GPS data, what's the riders and who is the drivers and what's the city, etc. So the whole data point is traceable. So out of the 6,000 of the serious incidents, every single one is built like this. And actually, every single incident in Uber is actually not built like this. So it's totally traceable. If there is a uncertainty, just an unknown for the incident, the agent can, the data analyst can identify each single incident and trace all the support tickets related to it, and what the life cycle transition it went through, and what are the auditory responses it is. And we snapshot this table daily, along with its corresponding support tables, smaller tables, dimension tables. And the whole process is fully automated because it's beyond one person's capacity to actually track each individual ticket, or the billions or millions of tickets. And this is actually agnostic to platform and agnostic to the technology and agnostic to product lines. The reason is that we actually we actually has several ongoing technology and database migration and even internal service migration. But now this migration should affect the final result here. And the only thing could affect final result is taxonomy classification. So we always make sure this rerun with the newest taxonomy classification. So because of this very unique data quality project, we actually learn a lot of the learnings from it. Generally speaking, the problem could be generalized as identify data of interest out of a total data set of billions of data points, define a life cycle for the data, and enforce the data in a consistent way. This is our 7 principles I summarized from this project. The first is always favor simplicity. The real world data problem is in such a complex state, and we should be crystal clear what's the goal and how to get things done correctly in a short period of time. In this case, we define the problem as a finite state machine and build tons of data lifecycle controller. And each controller is just doing a very specific and simple task to enforce the finite state machine from state A to state B. For example, it can be from to be corrected to corrected, something like that. The second is that we need to be crystal clear about single source of truth data. Because we do have different data access pattern in Uber, there are at least 5 copies of the same data in different places or different formats. For example, the source of truth data is in web application, but in order to serve it, we also save in database, transactional database, in Kafka, in Hive. They will be eventually consistent, but at every single moment, there are data discrepancy on different platform and different data stores. And this is actually quite normal in any data-driven company, in any tech company in Silicon Valley. So that's why we need to be crystal clear about who is the single source of truth data, which is actually single source of truth data, and embrace the change. I think the change can happen at every single level. During the 2 years journey, we originally thought to actually classify only sexual misconduct data. But after 3 months, after we classified the 500,000 data, then we got a problem. What about other type of incidents? What about incidents in other regions? Then the project scope keeps expanding and changing a few times during the process. And some incidents could keep updating even years afterwards, especially for serious incidents. So in this case, we should handle the change and embrace the change. And underlying technology, we actually changed several times. There are 2 to 3 database migration even during this journey, from Cassandra to Schemaless to DocStore. So we also have compute engine change as well, from Hive to Spark, and also underlying service provider change. But now this should be reflected on the final data side because it's not business related in this case. So there is a fun fact that at one time, we noticed that there are 4 services in the loop, and every single service needs to be upgraded and will affect the upstream and downstream. So we have to figure out how to upgrade it without breaking the whole loop. Usually it's a dependency with other teams and request we actually update the service. So I think what we learned from this journey is the only thing didn't change is change itself. And due to change, we favor a much flexible solution like Lego sets. Basically, you allow user to assemble and use them based on their needs. It's very flexible. It has unified interface. You can assemble and use it differently, just like the flexibility of the tool. And additionally, what we learned from this is also, unlike software release, data release is subtle and hard to version control. If you think about the data scientists and data analysts, they always favor to use latest version of data. So, and different organizations communicate through data. So this is like a data mesh concept. Everything should communicate through data. So as a safety data team, we think the data is like running water. We never know when our customer gonna from which organization will use the safety data for what purposes. The only thing we could do is keep the data fresh and of good quality. That's why we trace and snapshot every single table in this case. And in this case, the snapshot of the data is actually similar to software release, except it's actually snapshot daily. Since we build the whole process like a finance machine, so it's beyond humans' capacity to track billions of data points life cycle, and that's why we actually automated everything. It's quite important. I think the number one lesson we learn how we make this project doable is just actually automate everything. At the end, it's just your statistic is actually just related to this project, because think about it. All these 6,000 serious incidents, it's actually very easy to find false positive from this few thousand data points. But it's also very hard to find the false negative data points from the rest of the billions of data points. So what we do is use a combination of NLP, natural language processing, and statistic, and a 95 confidence level. For example, we could break down the tickets by category, like if it's dangerous driving, by a time range, like for example, 2017, April 1st, from 1 to 2 p.m. By location and by time of the day, and sample enough data points and audit. So this will give us an estimated percentage of false negative each data point has, like each category, each bracket we have. Then we can further break down the data until we find all false negatives. Actually, out of these 35 million audit, majority of that spent on finding the potential false negatives from different bracket, from different category, and from different location and time range. Okay, so shameless plugging, email me if you are very interested. So what we actually apply, what I learned during this, and what we actually apply these principles and learnings to solve the data problem in Web3. So ZettaBlock is building essential data platform for Web3 field. So this is actually a much interesting problem than this one, and it's a bigger project than this one as well. So email me if you're interested. Thank you.